Okay, hello viewers. This is what you're welcome to Illuminate What Tutorials. I'm Stanley by name. So today I'll be taking us a topic in physics, which is elasticity. Now, before we move on, what is elasticity? Now, elasticity is the ability of a material to regain is original shape or dimension after when the force applied to it is what removed. So that's what elasticity, the ability of a material to regain what is original what shape after the force that was applied to it that stretches it has been removed. So that's what elasticity. Now, the elasticity can also be represented with a graph. Now, what do I mean by the graph? Since elasticity has to do with what extension and what force. Now, when a tensile load is what attached to the material. Now, let's what plot. I draw the graph. Now let's just say force versus what extension. Now the graph will be what linear if the load is what small. Why it will not be what linear if the load is what large? Why? Because if the load is large, there will be a point it will exceed what is this elastic what limit. Now this is it. Now if it's now called now this is the linear one. That shows okay. Let's just say if the load is small, this is how it will be. Now when the load is not large, it will now curve to a point. You come to this place. And this place it will curve to is now what the elastic what limits. Elastic limits. Now the point it cannot what regain is what original shape again. That's what we mean by what elastic limit. Then at some point it now gets what a point what we call yield point. Now the yield point is where it was lost is what rubber property, where it can no longer what stretches again. Now after that one we now have what the maximum what load. The maximum load. Now the maximum load is the point I get now where it can no longer what this is the total or the load that it can what this the material can what entertain. And after this place, it will now what cut. Then after this point, this is what the load that the thing can what entertain. They'll say, I'm not going any place again. You don't do. This is where I can go. Now after this point, you now get to a point what we call the fracture what point. Where it's this thing now what cut. You can experiment it. Fire a rubber, drag it. You get to a point that when you are stretching it, you can see that the thing will what extending. And after a point, you see that the rubber will cut into two. That's the point where the rubber cut into. That's where what we call the fracture point. Then the point that the thing get to, where it can no longer what stretches again. I get now is what this maximum what the maximum load. Where the thing is now so tight. Then this point is where it's no longer drawing again. That's it has lost his what rubber property. That's what the yield point. Then this elastic limit. After you now release it, no longer will go back to the original position. That's the elastic what limit. Now let's now move on. Now there is a law governing what elasticity, which is known as what Hooke's law. Hooke's law. Now, what is Hooke's law? Now, Hooke's law states that the extension of a material is what directly proportional to the force applied. I get now, provided that the elastic limit is not what exceeded. Now, if the elastic limit is exceeded, that means it's not obeying what Hooke's law again. That means the thing cannot. If the elastic limit is exceeded, it's no longer what obeying what Hooke's law, and that's Hooke's law. Now, Hooke's law cannot what be mathematically what stated. Let me just stop here. As f. Now, since it's directly proportional to the what extension, now if the proportional sign is removed, there is equals to be what introduced, and the constant will also be what introduced, which is now what ke. That's this is force, and this is what the constant, and this is what the extension. Now, force is Newton. Now, if you want to get the SI unit for constant, you make what constant set of formula. So divide by what e, divide by what e. E cancel e. Our k is now equals to what f over what e. Our f is what Newton. Then our extension is what meter. So our extension will not our SI unit will not be SI unit will not be equals to Newton per meter or Newton meter raised power minus one. No minus one is same thing as times 1 over what m. Now how which is 2 that is here to be 2, but since there is 1 here, so 1 just simple 1 is still the same thing. So that's just the meaning of this raised power minus 1. So that's been said for the Hooke's law. Now let's now move on to the other properties under elasticity. Then we have the what the tensile what stress. Tensile stress. Now the tensile stress is equals to force over what area. This is the force. Now force is what Newton, and area is what meter what square. So the SI unit is now equals to what Newton per meter square or Newton meter minus what 2. So that's what SI unit. That's the tensile stress when a tensile load is applied to it. Then we now have what the tensile what strain. Now the tensile strain is what the ratio between what extension and what length. Now since length is what meter and extension is also meter, so the meter will cancel what meter. So there is no what SI unit, no SI unit for what strain. So we now move on to what the Young what modulus. Young modulus. Now the Young modulus is what the ratio between the tensile stress over the tensile what strain. Tensile what strain. Now we can go further. Now we can go further. The SI unit is Newton meter what cube. That's for the tensile stress. Since the strain doesn't have what SI in it, then we can solve for that. Now the tensile stress is what F over what A, F over what area over what E over what length. So solving further, we now have what times. You know, a fraction divided by a fraction. For it to cancel the division sign, you have to what bring the denominator of the down or the fraction that is down up and the numerator what down. Then we now have what L over what A over E. So which is now equals to FL over what A E. So this is also known as what the Young modulus formula. You can see it in your OBJ. Then that one be said. Now let's now move on to the potential what the work done. Now the work done on a what on an elastic material is equals to the work done on an elastic material is what average force times what extension. Now our average force will now be what 1 over 2 F what E. That's the work done. Then we can solve for that since our F is equals to what KE. No, let me write it. Since F is equals to what KE. So anywhere we see F, we can put what KE, replace it what with KE. So if it's being replaced, you put KE here, it will now be what 1 over what 2 KE what square. So either this or this. So depend on what you were given. If you were given force and we're not giving constant, you can still solve for that. So that's all for this one. Then we now have what the potential energy. Now the potential energy is the energy what stored what in the elastic what material, or the potential energy of the elastic what material is equals to the what work done. Now you know the work done is the work done on the elastic material, while the potential energy is the energy was stored in the what material. So it will be equals to, now the potential energy is still the same thing as 1 over what 1 over 2 Fe or 1 over 2 Ke what square. So if you're asked to look for the work done, look for the potential energy, it's the same formula for the both in elasticity. Now, with that being said, now what if in that tensile stress you were not given area? Now the area of what of a wire or a bar is equals to, if you want to calculate it, per and diameter square over what 4. So memorize the formula. It's not a question that they will give you the area. So you sometimes you have to calculate the area by yourself. So this is what the SI for calculating the area. Now let's now solve the question on the board. They said an elastic string stretches to what a total length 30 centimeter. Now let's write the parameters. When you are given a question like this, it's better you write the word parameter first. So the total length. So the total length is equal to what 30 what centimeter. Then they now ask us again. They said under what? A load. So the load or the force. Sometimes they use load and sometimes they use weight. So 500 what? Newton. Then with an additional what? Load. So this one is now what? F2 or load 2, which is what? 100 what? Newton. Then I said this. Then this stretches by it stretches by what? It stretches further to 2 centimeter. This stretches by what? A further what? 2 centimeter. That means extension or extension 2 for this force is what? 2 centimeter. Now this place now, this total length includes what? Since it was under a load of what? 500 newton, it includes what? The natural length and the what? The extension when a 500 newton or 500 load is what? Hanged on the material, hang on the string. Then they now ask us to look for the what? The natural length. You know we can't calculate the natural length until we get the extension inside this 30 centimeter because this is the total length of the what? The string. But the string now has what? An extension under inside it because of this 500 newton. Now for us to now get the natural length, now we have to calculate the extension inside this what? 20 what? Centimeter. Now for us to calculate this, you can calculate the constant, then you can use the constant to calculate what? The extension with just this two, with just this. You know you're not going to make use of this one because it's the total what? Length with extension. Now for us to now calculate, we now know that F is equals to what? Ke. F is equals to what? Ke. Now you know that F is what? The force, K is what? Constant. Now we have the force and we have cost. We don't have the constant. Now let's make what? K so to what? Formula because of what we have here, the parameters we have here. So divide by what? K. So our extension. No, 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 no. Sorry. Let's make what? K solid formula. So divide by what? K. So our K is now equals to what? F. F is equals to what? F over what? E. Our K is equals to what? F over what? E. Now, with this now, since we have two force, we can what? We cannot solve further. We can replace this K with another what? Force over what? Force over what? Extension. So now what? F over what? E is equals to what? F over what? E. There are two ways you can solve it. Then, what is the first force? We have what? 500. We don't know the extension. So we are looking for the what? Extension. Why for the second force? We have 100. And what is the extension? 2. So cross multiply. So if you cross multiply, this one is what? 100 what? E is equals to what? 1000. So divide by what? 100. So divide by what? 100. 100 cancel 100. So our extension is now what? 10. So 0 cancel 0, 0 cancel 0. So which is what? 10 centimeter. Then for us to now calculate the natural length. So the natural length will now be equals to, the natural length will now be what? Therefore, therefore, the natural length is equals to the total length minus the extension, which is what? 30 centimeter minus what? 10 centimeter. So our total length is now what? 20 centimeter. If you convert it to meter, it should be equal to what? 0.2 what? Meter. So that is all for this one. Now let's now solve what? Question 2. Now the question 2 says that a stone of what? Mass 20 kilogram. Let's write down the parameters. Mass 20 what? Kilogram is what? Projected vertically upward with a catapult anyone cord, rubber cord, has what? A force constant. Then the force constant on the rubber cord is equal to what? 72 Newton meter. I said if the tension of the cord in the cord at the point of release is what? 36. So our force is equal to what? 36 Newton. The velocity of projection of a stone is what? We don't know. Now, looking at this question very well, they said the stone and a catapult. Now, a catapult has what? A rubber. Now, that rubber, that's when what elasticity would come in. Then the stone, that's where all this energy comes in, like potential energy. The energy acquired by virtue of what position is what potential. Why the one acquired by virtue of what movement or motion is what kinetic. Now, if you look at this very well, they say a stone of what mass, it was projected vertically. Then the stone was what on a motion under what free gravity. That means we are going to make use of what of the what kinetic what energy of the what of the stone. The kinetic energy of the stone will be equals to the what the potential energy of the what rubber cord, because the rubber stretches, that's where elasticity come in. That will now give us the constant for the rubber and the force for the what? The rubber, the tension at the point of release. So we cannot calculate, since there is the relation between the stone and the what catapult. So the stone has what a kinetic what energy when it was projected vertically, which will now be equals to the potential energy of the stone is what mv square, then equals to the potential energy of the what of the rubber cord, because the rubber cord wasn't moving, so is what on a position, so it's not moving, so we can't make use of the there is no even kinetic energy for elasticity, is potential. Why? Because virtual what position here is staying. So we now have what what is the potential energy of what of a material, of an elastic material. We did it the other time. We said is equals to half what ke what square, or half what fe. So let's make use of what half what ke what square, because we are giving constants. Now, looking at this thing, we're not giving extension, so we can calculate the extension, or we can decide to what look manipulate this formula, not manipulate actually, make e solid of formula using the normal formula, the Hooke's law, which is F is equals to what ke. Let's make it what e solid of formula. So divide by what k, divide by what k.